the the research manager. It is my pleasure to introduce our distinguished speaker, Dr. Humayera Islam. Originally from Bangladesh, Dr. Islam has a rich academic background with a bachelor's and master's degree in applied statistics from the University of Dhaka. She later pursued a Master of Science in Health Informatics and doctoral degree from the Institute for Data Science and Informatics at Missouri, where she has made a significant contribution to this field. Dr. Islam has received numerous accolades, including the 2021 AMIA Student Design Challenge Award and the 2022 Best Student Paper Award. She has also had key leadership roles such as the president of the MUIDSI Graduate Student Organization and chair of the Student Working Group at the American Medical Informatics Association. Please join me in welcoming Dr. Islam.
Thank you so much for that generous introduction, Dr. Kim. I took your course one semester, if you remember me from that course when I was doing my master's. Okay, I think I'll share my screen. So let me know if you can see my screen well. So you're able to see my screen, right? Okay, cool. Thank you. So good afternoon, everyone. I'm really great. Thank you for having me here today and giving me this opportunity to present my work. I just defended my dissertation, my PhD dissertation, a couple of weeks ago. So I'm a little fresh, but yes, thank you for giving me that generous introduction. But still, I was thinking, before we begin, I'd like to introduce myself a little further, give everyone like an idea of like where I come from and what I have been doing. So I started my PhD in health informatics in the year 2020. And before that, I have a master's in health informatics, and Dr. Kim mentioned, and also I have a bachelor's and a master's in applied statistics from Bangladesh. So during my PhD journey or in the journey in graduate school, I do have some collaborative work, some research publications, and also have a lot of collaborative papers published and some conference presentations as well. During this time, I got some notable awards during my PhD journey. One of the important ones, like the MISU 18 honor that I got in 2023, Outstanding PhD Student Award in 2024, and all of that. So, I'm also very involved in different leadership roles. So currently, I am serving as the chair for the Student Working Group at the American Medical Informatics Association. So yeah, and now let's begin the presentation. Today, I'm going to talk about AI-driven prediction of diabetic complications, navigating EHR complexities. So this is mainly my PhD work, like entire graduate school work. I would like to summarize it as that. So this is the outline of today's presentation. And let's begin with the brief introduction of the clinical domain of this work and how I ended up working in the diabetic domain. So this is this presentation, I thought I'd keep it like a way of like talking through the journey and the evolution of my research work during my time here in the graduate school at MU. So while I was developing my research goals as an informatics trainee, my focus was on bringing innovation both in the clinical scope as well as the informatics scope. To determine the scope of my work, I had to first assess through what resources were available to fully leverage their potential. Then I had to determine the clinical domain I'd like to dive into. So when I started my PhD, or as well as my master's as well, our lab had access to the Cerner Health Facts database until 2021, and then we got access to the MU Electronic Health Records data lake beginning of 2022. So the clinical domain that my research was mostly focused on was diabetes, which is this is a diabetes collaborative diabetic lectureship series. So yes, we all know the importance of this chronic metabolic disorder that affects over 37 million patients in the US. just to give a definition of how I understood it, is that it's an impairment in regulating glucose levels in the blood, leading to excess flow of sugar, which lets that excess flow of sugar can slowly damage the end organs, increasing the risk of developing multiple complications among diabetic patients, which makes diabetes management complex and financially burdensome. So this led me to work more towards developing predictive models. I was interested in this domain, like as many of the applications of such predictive domains was to improve the overall healthcare outcomes. So that drive me towards that, what are the diabetic related complications and how it's impacting the overall healthcare, and if we can do something to to resolve that issue. So predictive models, like most of the predictive models, they work on predicting the risk of diabetes, of developing a complication. They identify high-risk patients, also identifying the risk factors. So most of the research that occurred in this developing the predictive domain world, it happened because of, a contributing factor was the massive influx of data in the form of electronic health records data. So in simple terms, EHR is a digital version of a patient's paper chart. But in recent times, it is much the scope of EHR is much more, because it provides you a standardized structure to organize the different components of care. For example, demographics, encounters, and this is one of the examples of the PCARNet common data model, that one of the ways of you are organizing the data into a data model that's a standardized model for doing research. So as EHR, is temporally extensive, the standardized structure provides us a lot of information over time for each patient. The question was, can the patient records reflect disease progression? So, or can EHR provide any important relevant information regarding that? So what we found that EHR is a valuable resource. The components of EHR can help identify patient cohorts. They can be used as features for prediction, and the overtime visit data provides enriched temporal information on patients. However, there are some challenges and complexities. EHR data can be both dense and sparse. The patient visits occur in irregular intervals. There could be lots of incompleteness and missingness in the data. So how do we use this information and overcome the challenges? That's one of the questions, or the questions I had at the beginning of my research. So what we looked at, in traditional research in EHR, what we mostly find out that individuals are represented by a vector of attributes or features, and mostly those features are extracted or selected based on experts' opinions. There are models like statistical models, right? They're used for mostly focused on risk scores using relevant features, and those features are very hand curated, and sometimes that could limit your new discovery of knowledge, data-driven knowledge. So, and then came machine learning, which was mostly, when there were many features, those were very correlated. To handle all, also big data, machine learning came into play. So how do machine learning models treat our EHR data? So this is a representation of how it usually works. You have the EHR database, and you extract features from those the database, and each patient is represented by a row that contains all the features that you extracted. And that feature table is then converted into a large feature matrices, where you have lots of zeros and lots of ones, right? Whether it's a numerical or a categorical variable, the representation is almost similar. Sometimes for numerical variables, there could be standardization and other methods done, but eventually those are large feature matrices that you train through machine learning models, and then you are trying to predict labels. That's what we usually do in the world of machine learning. So what efforts have we seen in developing diabetic complications risk models in the literature? We found out the major applications was to predict the risk of each complication separately. Some of the studies tried to identify some risk factors, while model performance comparison was often the highlight of those applications. This leads us to my phase 1 goals, the first 3 publications that you see here. all these studies, we attempted to use various machine learning and advanced AI techniques like federated and transfer learning approach to predict the risk of diabetes complications. And we were focused on kidney complications among diabetes patients, retinopathy, and neuropathy. The common patterns in all these studies, what we see here is that we predicted the risk of each complication separately using different models, and all these studies were mostly focused on comparing the accuracy or comparing the model performance. So that that's heavily what was done in that time. As we saw in the literature, and also what we did in the phase 1 goals of my research. So based on the research and those publications and the evidence in the literature, I myself identified some gaps or limitations in the way we were looking at the data, especially looking at the EHR data, or trying to extract information out of it. So what we saw, that there were limitations in clinical relevance, where most of the models were treated as black box. So sometimes we don't know what exactly that model is trying to tell us, but we just know that which model performed better than which one. So, and most importantly, what we found out that we are trying to oversimplify the EHR to extract the features out of those, the EHR tables that we have, or the data we have, right? So we are disregarding data sparsity. We are not even considering the visit irregularity, somehow trying to simplify the temporal components into the temporal order into a non-temporal data that's helping us to do those predictions. So that oversimplification of EHR components is something that really caught my eye. And the key insights from those phase 1 aims and the papers that I published in the beginning of my PhD and also the existing literature that motivated me to change the course of my research a little bit. And my question was more steered towards that, can we address those challenges that I found out, or using more advanced AI techniques? And that led me to formulate questions, as you can see here, my research questions. And my entire goal was how do I seek answers to these questions? I want, what are the questions in the clinical scope, questions from the informatics scope? From the clinical scope, what I was thinking, I want to predict the risk of the major complications of diabetes for each patient using EHR data. And can we identify the global and individual level risk factors for diabetes complications? Is there a way to do that? Global and both patient level risk factors, it's something that most of the models, they tend to overlook, that they are not really explaining the results. So can we do that? And from the informatics scope, what I was focused on, that can we build a multi-complication prediction model that optimally utilizes the EHR features? We don't want to oversimplify the EHR, and then we want to see how much randomness or how much, including EHR as is, or the rawness of EHR as much as possible, can that help us predict? And then how do we capture both contextual and temporal order in the EHR? We don't want to use non-temporal representation, and also overcome the subtleties of EHR, like irregular visit intervals, sparsity, and all of that. And at the end of the day, is our model explainable? So research has shown that deep learning, the popularity of deep learning is based on that it can crunch huge amount of information, less processed and more raw, and they're less susceptible to correlated features. But what we were seeking, what I was looking into, is that I was looking for a method that not only can handle high-dimensional data, but also can capture the nonlinear relationships among features, capture long-term dependencies, overcome the EHR data-related issues or concerns, as I mentioned, don't want to oversimplify, and then predict more than one output at the same time. So that took me, as I was steering my direction from machine learning, I went towards deep learning. So now let's look at the advancement of deep learning for disease prediction, or how does that world look like? The initial efforts, as you can see, most after machine learning, when people started to do deep learning using EHR data, most of the efforts were to prove that yes, deep learning works. It outperforms traditional machine learning. And then people slowly started, like the researchers, they slowly started to discover different kind of limitations with different kind of deep learning applications. And things started to evolve, like, what we can do better. Is there any way we can capture EHR data or not oversimplify it, or capture the other dependencies of the EHR data, like long-term dependencies, temporality, dynamic contextual, context error, feature representation, and all of that. So every method that, people like the researchers, they were trying out and mostly applying to this field of building prediction models, they found out the major drawback of those methods was that training was very slow. And like a lot of times it also resources limitation was another thing that people found out that most of the cases limits them from using deep learning. As you can see, like deep learning and all these methods, they are developed in the natural language domain, not in other domains. Like most of the methods, they were developed in natural language, and because of the similarities between sequences in the EHR and natural language, there was a transferability of, techniques were transferred from the NLP domain to our EHR, structured EHR clinical prediction domain. So one of the biggest breakthrough in learning contextual feature representation in the NLP world happened with the advent of transformers in about 2017 and 2018. So that brought in a lot of curiosity, prompting researchers to adopt this into the EHR domain. And given one of the transformers or the large language models initially built was the bidirectional encoder representation transformers in 2018, 2019, because that paper, though it's cited like over 1,000 times, like many thousand times, but still that paper was not published initially. That was only available in their GitHub. And still people started citing it. And then they decided to publish that in a conference. So yeah, but this is one of the earliest structures of transformers, which is called BERT. So what happened that given this BERT, this attracted, since it is one of the earliest forms, people started to, see if this BERT, is there any way to adopt BERT into the EHR domain? So given the architecture of this BERT large language model or this BERT transformers model, and how it processes the inputs, can we, the researchers were trying to figure out, can we adopt it to our EHR domain? So the key element in this BERT is they have a very sophisticated embedding layer. So that embedding layer can capture nonlinear relationships among features. And also that embedding architecture or the layer design can we can utilize that to represent the temporal order of EHR. And BERT, this large language models, they all treat input as sequences. So that opens up opportunities of because each patient can have different number of visits, ending up with different number of, different lengths of information, and the model can somehow also work with that. So at the heart of BERT is the neural networks. So yes, that gives us the possibility of doing any kind of classification that you would want to do. So some researchers got motivated in adopting BERT to structured EHR data. As I mentioned, the structural benefit that they were getting, they tried to see if that fits the structured EHR world. So in 2020, the first paper was published. They called it BERT, B-E-H-R-T, where they used transformers or the BERT for for EHR data. That was the first demonstration. But this study is done by a group at the University of Oxford, and since then they published, out of the representation I'm showing here, most of the papers are done by them. The same group, they had different first authors, but they were working with the same kind of data set. And and UK, they have this CPRD data set that actually covers it's a big data set with millions of patient data, and they were using that to build those, to show those demonstrations of building prediction models using BERT. And as you can see, I tried to see that from two perspectives, unimodal and multimodal. Why did I do that? Because the first study used only diagnosis as features to predict them different kind of, different kind of diseases. So since they use diagnosis, like a lot of studies, still a lot of studies, they're focused on using only one kind of features. But soon after, people started to experiment that how do we incorporate other kind of features, because EHR comprises of all kinds of data. It includes your demographics, your labs, your procedures, and so many things. So they tried to explore if that model can accommodate it. And these are like different kind of experimentation. So, what we learned, or like what we see, what we saw in those most of the initial studies, that all of the studies, they applied a two-stage process. First of all, there was pre-training on extensive multi-site EHR databases. Like when we called pre-training, it means like we are training a model with a huge data set, like huge that covers a huge population. And then when you have trained the model, it's by the concepts of transfer learning, you use that model on smaller cohorts for clinical predictions, and that is called fine-tuning. So all of the studies that you see here, they're all done on two-stage process, like extensive multi-site EHR databases, and then on smaller cohorts for clinical predictions. However, there is one caveat on that, like the pre-trained models from the previous studies, they're not easily shareable, unlike most NLP domains. As people, we right now we know that all of the big companies, whenever they have a pre-trained model, they publish it, right? They want all the people to use it, but that's mostly common in the NLP domain. But when it comes to the EHR world, we are not that open to sharing our models, which may contain or which might be susceptible to information loss or privacy issues of the EHR information that we're using to build those models. So those models are not shareable. So most of the studies, like all the studies so far, they have talked about building the pre-trained models by themselves, but nobody can share it. So when you look into it, when you are building a pre-trained model and you're investing a lot of your, resources into it, that pre-trained model can be used to do a whole lot of different kind of clinical predictions, because pre-trained models are usually a very generalized training done on, data. So you can curate it and use it or fine tune it on different kind of tasks. But when it comes to the EHR world, that model is not shareable. So eventually the resources that they are building, they are very restricted when it comes to sharing with other researchers. Like for instance, if somebody is working with, say, proteomics, right? So they have a lot of protein structure model that are already pre-trained on huge, large data sets available for the users to use. So you download those models, you then use your data, whatever additional data you have, and then you fine-tune that model and then do predictions on different kind of tasks. But in the EHR world, that's not possible, right? Those models cannot be uploaded somewhere out there for everybody to use. And another interesting thing that I was about to say in the last slide, but I thought I would keep it for this slide, is that in the multimodal applications, what we saw that when they were trying to incorporate more than one diagnosis, more than one features other than diagnosis, like for instance, the numeric features, age, BMI, and other labs and all of that, they were all incorporated in the embedding design. So they were not really treated as features, but rather they were all incorporated in the embedding design. I will try to demonstrate what I'm trying to say here in a few minutes. So yes, so these are the things that we found out that, that in most of the literature, or summarize the literature that we have seen. So let's look into the architecture of BERT first. Here, this is the conventional pre-training and fine-tuning. As I mentioned a little bit ago, that there were two stages, right? The two steps. First, there was this pre-training task and then the fine-tuning. As you can see, the pre-training, the BERT model, it gives out outputs, and then you are able to do like, different kind of predictions. But the two tasks that you are, learning here for the generalized pre-training task is, one is mass language prediction language model, MLM, that's what we call it in the NLP world. And then there is another like a generalized binary classification prediction head. There is another like that. So that's how, when you have the pre-trained model, which is trained on generalized tasks, and the MLM task is a self-supervised learning task. The binary one is somewhat semi-supervised, or sometimes could be self-supervised as well. So and then when we do the fine tuning, you have that pre-trained model and you use it on putting any classification head on top of it. And then you are trying to predict, that classification head is helping you to predict. So if I look into the model, given what we see, how the input is processed, it's a little bit technical, but yes, the input sequence, it goes into the embedding layer that I mentioned, the embedding design, and then it goes through different various layers, the encoder stack, which is like the entire like stacks of encoders, and then finally you get an output that we it gives out usually two output. One is the output of the last layer of the encoder of that stack. Another one is a pulled output, which is the representation of only the first token or the first input of the sequence as an output. So, that got me, like this structure, that got me really curious, and I started further digging into it. So then my quest to seek answers to my, I got more curious. So I started asking myself these questions, that how can we modify the framework to be able to work with single center EHR data? As I mentioned at the beginning, a whole lot of things, when we start our PhDs, like what resources do we have access to? I had access to the MU EHR data lake when I was doing when I was doing this dissertation goals or aims. So that is a single center EHR data. So the question is, so far we have, the studies have shown that they were training on multi-site data and then fine tuning on smaller data sets. I don't have access to that. So can we modify the framework to be able to work with only single center EHR data? And next, the question was, what role does that embedding design play in the framework? That was another exploration thing, how is it impacting the results, and how important the design of that embedding layer is in our architecture. And also questions like, can we modify the input-output network for BERT and tailor to our clinical prediction task? And then another big question was, can we still work with numeric features? Unlike, we don't want to use that in the embedding or consider everything as tokens, as input, in our data, but can we find or explore, or is there any way to incorporate numeric features, so that it makes sense, so that it's treated as features? That, leads me to what I proposed for my PhD, dissertation or work, is that shifting from the conventional pre-training and fine-tuning paradigm, I proposed an end-to-end task-oriented prediction, which is called top BERT. This innovative approach, it concurrently optimizes the model for multiple specific prediction tasks. And there are tasks like, the self-supervised task, the one that I mentioned, like the MLM task. Then it also has a generalized, a very general binary classification task. And also you can add on top of it another head that is going to give me prediction of the task that I want, which is the sequence. For me, it's a sequence classification prediction head. So what was the overall goal is that, I want, my whole idea was, since I don't have access to more than one, I only have access to the one EHR, that is our MU EHR data lake. How can I utilize the entire architecture of BERT and still utilize those, the sophistications of embedding layer, the way it does training, and all other structural benefits of BERT, to my single center data problem. And that way, like this is what is like modifying the framework or modifying the architecture was the way to go. If you like, that was the overall model in the last, but what I was trying to say here, that the thing that we added or that I proposed to add was this sequence classification prediction head shown in this, this side. So eventually, when you are training the model for it's a multitask modeling framework, you can call it that way, but the background is BART. So what we are trying to do, like for, combining everything together, there is a combined loss that the model learns and back propagates into the model. And it's like, it's learning from three different, like it's learning, the model is learning three different things at the same time. So that is like, the combined loss is what we are training here. And that leads me to a little, like, give you a little bit idea of like the phase 2 of my research. So now the question comes, like as I mentioned, like the MU EHR P-Carnet CDM that I had access to. So I have the diagnosis, I have medications, I have lab measurements, I have the vitals, and I'm working on multi-morbidity or like the multi complications of diabetes. That is my end goal, like to be able to predict that. So now the question was that how do I propose the model enhancement that I proposed with top BERT? How can I tailor that to my clinical prediction task? So for the first demonstration, I focused on diagnosis. As most people do, we started with a single, like only one kind of features, which is diagnosis. And that leads me to the A1 of this phase 2. So the goal was to predict the four major diabetic complications: retinopathy, chronic kidney disease, major cardiac events, and the MACE events, and the neuropathy. So as you can see here, what we did, that the overall idea is to show or demonstrate the use of top BERT framework using diagnosis codes. So for simplification here, or reduce our dimensionality for the first set of experiments, what we did, we converted the ICD-910 codes of the diagnosis codes to Phi codes. That results, like, if you have over 30,000 unique ICD codes, if you convert that to Phi codes, then you end up having close to 2,000 codes. So that reduces the dimensionality. And we wanted that because we wanted to see if we can, because we were more focused on experimenting that if that works. So that's why we focused on a simplified, representation, which is converting the diagnosis codes to Phi codes. So another goal that we had was to compare the different embedding designs to identify the optimal temporal representation of EHR in BART framework. So here is a snapshot of the cohort that we identify. First, we had to identify the diabetes cohort using the supreme DM definition. And then we had to identify the different, define the outcomes using various diagnosis codes. And then we had to, this is showing what are the number of visits per patient pattern. You can see that most of the patients had less than 25, 30 visits. So, and then number of diagnosis per patient, as you can see, it's also dense, more dense within 50. Yeah, and we did have very balanced, gender-wise, a balanced data set, but not too much race-wise. And we know why, it's a Midwest hospital, right? So, and then, yeah, and one interesting thing is, as you can see here, we saw that since we extracted the diabetes population using supreme DM definition, and also which includes the use of medication, diabetes related medication, but they were not somehow diagnosed as type 2 diabetes or having diabetes in the data. So that ended up there are about 72.5% patients having type 2 diabetes. So the rest of the patients we extracted were patients using different kinds of diabetes related drug, and we use the full definition. So it's already a published paper, and the definition comes from there. So just to show that how did we do the data conversion here, or the data pre-processing. The first stage was to create a timeline for each patient. So the timeline comprised of all the encounters and up to for patients who had one of the four or all four or any one of the four outcomes, the four interested outcomes that we have for the study, we for those patients, any visit before that event happened or before that outcome happened, we took up to that point. So that was like the learning period, and that was the cutoff point. And we tried to determine whether that outcome happened within the 12-month prediction window after that last visit or not. If you can see it, say in simple words, if a patient is coming to the hospital, we are trying to see, using today's information, if the patient is going to have that diagnosis of those outcomes in the next 12 months. So that's pretty much it. Just to resemble that, we use that cutoff point. And then for patients who didn't have any outcome, we included the entire set of encounters for that patient. And then comes this EHR timeline representation then was converted to tabular data. So as you can see here, the diagnosis codes are represented by fee codes, and then that is the main thing that's important to understand, that how we converted that EHR database, the tabular information in the EHR, to sequences. So as we talk about large language models, they only understand sequences, right? So we need to find out a way to represent our structured EHR data into this sequence of information, and that is how we do it. Number 4 here on the on my infographic shows how we did it. We represented that the tabular into a sequence. And also we did tokenization. This is another interesting thing about NLP, that this tokenization means that we are giving unique numeric values to each of the diagnoses following a dictionary. So first, for since EHR diagnosis doesn't come from any dictionary, so we assume that all the diagnosis is comprising our dictionary. And all the diagnoses that we have in the fee codes, they are our dictionary, and everybody has a unique numeric number to it. So that is the number we are using instead of using the fee code directly. So yes, we used information as you can see here, age at every visit, and also number of days difference between the each encounters, and then also the number of visit as one of the information. So I will show in a bit how does the embedding feature look like, or embedding design look like, which is the next step. So as you can see here, as I mentioned, that embedding design is usually a very sophisticated representation of the EHR. So what it does, it has different layers. And the first layer is where we are including the diagnosis, the tokenized sequence of diagnosis. And on top of that, you can add other representations. Usually in the NLP domain, they use the last two embedding, the position and the segment embedding. So what these two embeddings are doing, it is giving the model a sense of the position of each of the tokens in the sequence. So for EHR, how do we understand which token is placed where? It means that, how do we characterize the temporality? So in the earliest paper, they used, position embedding and segment embedding, which is the regular, the NLP, what in the NLP world people do. But in some of the papers, they used age embedding, and a lot of the multimodal papers, they included all the numeric features here as different layers into the embedding design. So what embedding design, each of the layer is doing here, that it it actually generates weight matrices, and those weights are trained during the training. So it's a little technical to understand how everything works, but just imagine that every token, in the sequence, has a dense vector representation, and eventually all the embeddings, they get added up, and the sum embedding is your input that goes into the model. So how the researchers were thinking that the embeddings, for instance, the time difference embedding, the visit embedding, they are providing information about where that particular diagnosis happened, or what is the location or position, or what does that mean or imply to have a diagnosis of hypertension in the first visit compared to the last visit. So give the model an understanding of the position of that token. So that's what the different embeddings are doing. So in the literature, they tried different kind of embedding designs, but I didn't find any solid rationale of why they were using what. I do understand mathematically that the tokens the tokenized input, having those embeddings alongside is giving the model an idea of the location and the position of each of the tokens. But why the design is complex for some of the studies and why it's simple. So as I mentioned, I did some exploration along that line too in the study. So I'll cut short and talk about, this is a very a representation of what the results that we found in the initial experiments. So what we did here is on the left side, you can see the different kind of embedding layer design. So the picture, the thing that I showed here, it contains all the layers that we could consider as embeddings, but then I did an ablation to to include different combinations of that and to see how it impacts the performances. So what we found, there is another way that we try to see is using the information gain and entropy. We try to measure the entropy for each of the models, and comparing with the model that had all the embedding layers, we saw that simpler versions of those embedding designs were showed more information gain than the more generalized, having all of a very all the layers stacked together. So that was one, the panel B shows that result. And so as you can see, we were comparing TOBBER, that is the framework that we have, with another set of experiments that is using pre-training and fine-tuning, the two stage processes that are commonly found, as I mentioned before, but using single center data, because I don't have access to more than one center data. So eventually I had to do the experiments using the single center and try to see if there is any difference in model performances. So here I just noted one of the results, where we are using only two embedding layers, which is the time difference between the visits and the visit number, if it's a visit 1, 2, 3, like that. So that produced the better, that showed comparatively good performance here. We are saying comparatively, as you can see, most of the results were somewhere in the same line. So, but what is the difference here? Fine-tuning A and B, that requires first pre-training and then fine-tuning on smaller data sets, right? But TOBBER, which is only using the fine-tuned cohort to do the task-oriented training, that is trying to learn and predict at the same time, that is performing equivalently or similar to our pre-training and fine-tuning that's done on a single center model. So which means that saves our time, right? Because fine-tuning, pre-training and fine-tuning, two processes require more resources. But when you are using an end-to-end training for the single center data, it can provide better performance compared to pre-training and fine-tuning on that data set. So yes, that brings me to another another aspect of my work, as I mentioned before, for my PhD clinical scope and informatics scope, and also added the high performance computing scope. So using hypercluster GPUs, because all that I have talked about, they cannot be done in normal machines. You need powerful machines to do that. So here is an implementation framework that I try to show that how I utilize the Snowflake, the AWS Workbench, the Nautilus Hypercluster, and the PyTorch infrastructures all together, combined together to do my model training. So my data, like the MU EHR data, I accessed through the Snowflake. I did all the pre-processing using AWS, like a protective environment, and then I extracted the features and the labels, and then transferred that to the hypercluster environment. Here is the key point here, that to be able to do experiments like that in large scale, you need access to GPUs that are very powerful, that are, that can help you train your models faster. Or like you need access to not only one GPU, if you have access to multiple GPUs, that helps you to do, training at this like simultaneously. So that helps, that saves time. That's what happened in my case too. Like, I ended up, for this set of experiments only, I had to train about 75 different models. So if I would have waited to do them individually in one machine, that would have taken about 65 days. I'm not, like I'm telling you exactly the days of training, but when it comes to run these models, you have to do it 100 times to get to the right one, right? So that doesn't count that, but then 65 solid days of training, assuming that they were running right. And then with parallel training that I did, like, using all the GPUs and the hypercluster, I was able to do that in 2 days. So that was like really good when it comes to time, time management. So I built, as I told you, like, I did modify the BART model. So I had to modify the model framework. So I did the entire framework in PyTorch, showed it as a work, like this is the workflow that I have, used. I tried to show that in a pictorial representation. So what we learned out of it is that the key insights were that BART framework that can be modified to develop an end-to-end training and evaluation method that can perform multitask learning, and simpler temporal embedding such as visit number and inter-visit durations offered an optimal trade-off. And what we saw that what was our goal after that? To improve model performance and use more granular tokenization, that is not any mapping, and then integrating numerical features. So I think we are running short of time, but I'll try to go over like the modifications that I did, because the next goal was to incorporate more features, medications, lab measurements, vital signs. And to reduce the complexity of that problem, I focused on only the chronic kidney disease for that particular output. So yeah, the phase that brings me to the phase 2A and 2, where I was predicting chronic kidney disease. And then we were adopting the TOPBERT framework to include diagnosis codes, medication prescription codes, the RX norm codes, and also the LOINC codes as lab codes as input features. Then modify the TOPBERT to improve the CKD predictive performance using non-numeric features, and also explore ways to incorporate the numeric features into the prediction model. So as I mentioned, now I have two kinds of features, right? One is the non-numeric features, which is the diagnosis, medications, and all, and the LOINC codes, and the numeric features. How do I incorporate it? So the next set of experiments, we're only using the non-numeric feature training, but this time we are not only using diagnosis, but we're using medications and labs. And for the non-numeric designs here, I did another modification. Instead of using the pooled output layer, I used the direct output of the last encoder, and then put that head for the CKD prediction on top of it. So each time I do it, I need to modify the entire model framework. So just to be clear, like, I'm modifying the entire framework every time for doing it. So, and then this classification head actually included, a convolutional neural network, residual network inside it that was doing our predictions. And then moving on to the numeric feature training, what I did, like I considered the vital and the lab result table, firstly transformed that into tabular format, and then represented the numeric features into a 2-channel array. Like the whole idea was that one array is going, like one matrix is going to show us all the numeric features that that are available in those tables, And then the time steps and the encounters is this on this axis, as you can see. And the other channel was giving us more information about the data, that is the inter-visit time intervals. So using that, we used the cumulative time intervals those were extracted for each lab value, and all the missing labs were masked, and the dimensions, to match the dimensions, everything was padded. So we masked all that was missing, and we didn't do any imputation for this. So what we did here is, as I showed, firstly, the representation of the numeric features was important. We represented it into this array. Then we did a convolutional structure, a CNN structure, and then we was trying to predict it. So as just to be clear, if everybody's on the same page with me, that we are talking about two sets of experiments, right? Non-numeric features and numeric. So when we did the non-numeric, we are talking about BERT, but when we did the numeric, we are talking about CNN. So the missing piece right now is, how do we combine everything together? So here is one of the representations, like fusion of, the two models. How this includes both the numeric and the non-numeric together. So as you can see here, our input features consisting of two kinds of features, and the numeric features going through the convolutional layers, the tokenized sequences going through the BERT layer, and then there is a point where everything is summed up, or everything is combined. So that's, when we were able to introduce this architecture, that opened up more opportunities, to do so many kind of different representation of the model and so many kind of experiments. So I'd like to show some of the results like this, some of the results here for the study, because we are one of the paper is in the preprints, another paper we are currently working on. So here, just to give an overview what's happening, that when we use only the diagnosis, as features, this was this was the results of the AURC and the AUPRC. When we combined diagnosis with medications and lab codes, so here, that the AURC is, because I'm talking about only the chronic kidney disease here, not about the other diseases. So that's why the result is not exactly in the table, because that table was showing the overall AURC for all the four outcomes, but here it's mostly focused on chronic kidney disease. So what we saw when we included medications and lab codes in the BERT model, our performance improved. Like both AURC and AUPRC improved significantly, right? And then when we did only experiments with the numeric labs, we saw that the AURC was very high compared to the other models, but the AUPRC, the precision recall balance, was not as good. So, and now the work in progress, as you can see, that is the combination of the two models, that how do we combine the two models? And that has a lot of ways, we can experiment in so many different kind of ways there and introduce so many different kind of model combinations, And for when we did, in the best result that we got was that had an AURC of 0.7101, but then again, we were struggling with the AUPRC balance. So now the question would be, how do we improve the AUPRC? And we are trying to experiment different kind of ways of combining so that eventually we are also able to improve the PRC. So that's mostly about the model comparison. One thing I'd really like to go over a little bit about is, how do we use these models to explain the results? So that was one of my aim 3, and I utilized a method called integrated gradients on the top BERT from the aim 1 to do some explainability of the models. So here is one of the representation of global level feature attributions common for all outcomes using the integrated gradient method. So and also we were able to identify some global level feature attribution for each of the outcomes, like what are the comorbidities or what are the other diagnoses that are leading to these outcomes or as picked up by the model, predictive. And also the age-specific global level feature attributions, we were also able to identify that whether there was a variation in it. But what mostly we found out, what did the result tell us? it told us a little bit about the documentation bias in the EHR. What we found out that a lot of times when people visit to the hospital, like for instance, a person has eye problems, so the person comes back to the eye doctor, eye doctor, eye doctor. Eventually, that person ends up getting a diagnosis of retinopathy faster than any other patient who's not coming to the eye doctor, like visiting the eye doctor that very much. So there is a pattern in the way things are recorded in the EHR that is the biggest limitation for sure. That we have to use the data we have at hand, and that's what we had, and that's what's telling us that there could be a documentation bias in the models, and that is something beyond our control because that's how the EHR data gets recorded. So yes, the overall in the phase 2, what was my key contribution is that I proposed that transformer-based framework for multitask learning within the confines of a single center EHR dataset with limited sample sizes, and also proposed further modification to the framework to augment numeric features into the model for clinical prediction tasks, and also demonstration of explainable AI model that validates the clinical applicability of the findings. I view my scope of work as a trajectory I built for myself, like a trajectory of research. So I believe I have just started. Although PhD for like 2 years of master's and 4 years of PhD training, after that, I realize I'm still just starting. So yes, that is the thing. Like my goal is to further do research on this model integration. How do I increase the scope of my work? How do we incorporate more, more EHR databases into this framework? And just building the scope of what I do. That's what my overall goal is, and enhance, my skill set by working with multimodal data, like not only focusing on EHR, structured EHR, but including clinical notes and all of that, like genomics information and all of that. That's like my entire my goal. And then definitely I'm currently in the process of my eventual goal is to join the academics. So I would be happy to train myself to get there in the future. So yeah, that's these are the references that most of the work was inspired with. And thank you everybody for listening. Exactly, it's 1 p.m. I'll be happy to answer the questions.